My name is Lukas Will, and I will give you a short overview about the improvement of our charging circuit or charging board for the shooting mechanism in a soccer robot of the MSL. First, my motivation and my goals. Our goals were a more reliable circuit, because our old board had a lot of problems with communication or with broken parts, so we had to restart the board quite often, and that was quite bad before some games, so we had to get the robot out of the field, restart the board, test if the communication works, bring it back on the field if it works, if not, do some troubleshooting if we don't find the problem, put out the board and measure something. It was quite bad, so a more reliable circuit. The second term was galvanic isolation as a goal, because we wanted to achieve a greater security or safety for people to work with it or work on the robot. Otherwise, you shouldn't work on the board if it's fully charged. Our next goal was a modular and flexible board, maybe to integrate it in some other robots, not only ours of Carpe Noctem. Therefore, we want to reduce the effort if there are needs to change something. On the one hand, the charging voltage or output voltage, or the speed. So if we want to to charge faster, then we don't want to reinvent a new routine or redesign a new routine. And with the old board, we had not so good regulated output voltage. It was between 320 and 330 volt. And so we had different energies in the capacitor, so we don't have constant flight curve or range with the ball. So we want a better regulated output voltage to achieve or to reach repeatability of the flight curve. And one point, the last point is the improvement of the energy efficiency, because it's a system which is based on batteries, and they are limited, so I want to reach, or one of my goals was to reach better efficiency, so we had more energy left, or we can use smaller batteries. That was our old circuit board. On the left side you see the logic part, and on the right side you see the booster or charging part with the coil, which it was a boost converter, and the coil with the diode boosts the voltage up to 330 volt. And the capacitor is external, it's a bigger part, which is not on the picture. Then we have the scheme of the old board. We have the boost converter, which boosts the voltage from 24 volts to 330 volt. And the voltage is monitored by the microcontroller unit, and the microcontroller unit controls the boost converter. Then we have a table, a hard program table, which tells the boost converter how we should switch the transistor. So that we don't borrow. We have one protection and discharge unit included that switches or that release the discharge of the capacitor if there's some over voltage. It was not fixed here. The circuit switches between 335 up to 350 volt to protect the capacitor, because it's limited at 350 volt. And there's no communication between this and the MCU. And at least the MCU controls the switch to shoot the ball. Then, questions up to here? Okay. Then we have the picture of a new prototype board. We have here it's controlled by an IC over an flyback transformer. And yeah, so we have a galvanic insulation because of this transformer, and the feedback loops are done by an amplifier, but an isolating amplifier. So the scheme of the new circuit board is a bit more complex. We have a lot more communication. We have the flyback transformer controlled by the charge IC, or not controlled, it's regulated, because we get a feedback loop from the secondary side. And the MCU is only there to monitoring everything, or a lot of things, the input voltage, the charge IC, and also can send start-stop messages, or not messages, but it can send a start and stop signal to charge or not to charge. We monitor the output voltage, and we not communicate, but we can get signals from the protection discharge circuit. So we know when the board, or when the output voltage is over the limited voltage. Break. Oh, let's go. Yeah, then we have some technical data. The old board, and the new charging board both work with 24 volt. The input current is fixed at the old board at 1.35 amps in the average. And the new charging board is not yet in the prototype version, but later it should be adjustable up to 5 amps, or a peak current up to 50 amps. And the charge voltage up to 450 volts for the new version. The old board is stable on 330 or 320, up to 330. And the charge time was in the test 16 seconds, and with the new charging board at the maximum speed we can reach for 450 joule, and the capacitor we can reach under 5 seconds. But only calculated, I tested it, not yet. Okay. Yeah, and the size is nearly the same, but there's some space left to compromise it, or compromise both. And then we have, I've marked the adjustable components. Here we have a resistor. If we add some more and reduce the resistance of the part there, then we can we can switch greater currents and can boost faster. On the other side, on the secondary side, the charging voltage. If we change the voltage divider, we can boost at higher levels or at higher voltages. And that I want to change to plug-and-play components, so that you only have to pick one smaller board up and put another on, and then you can boost at another voltage. Yeah. So the advantages of the new board, which I tested so far, is a more precise charging voltage, not a difference of 10 volts in the output. When I measured it with the voltmeter, I got a very accurate output voltage. I think if I measured it with an oscilloscope, then I get a voltage range to 0.2 or 0.5 volts. Yeah, then we have the galvanic isolation and a separated 300 volt circuit. So we have a greater safety for people who work on it or who get in touch with the robot. They had to touch the ground side of the 300 volt level and with 300 volts to get in danger, and not only if they touch the frame of the robot and maybe they shouldn't come to or touch the 330 volt, but maybe there's a broken part or something, then it didn't destroy our robot. Yeah, and in comparison to the old board, I've added Ethernet connection so that we can plug an Ethernet cable on the board to communicate directly with the IPC or industry computer we use for calculating our plans. So, and we don't need the way over the campus. So at first, or now we have the communication from the computer over a smaller board, which put the Ethernet connection or the USB connection to campus. Yeah. And the last advantage is the easy integration in other robots. So you only have to plug, or should be able to plug in future, the components to the consumption of current. So to say, okay, I want only peak current up to 20 amps, and an average current up to 2 amps, and then you adjust that for your robot, and adjust on the other hand the output voltage at maybe 350 or 400 volts, and then yeah, you can use the board if you get the communication on the MCU. Yeah. And we also have unfortunately some disadvantages. The new design is more complex, so the troubleshooting, if there's a broken part or if there are some errors, is more complex. And because of more parts and more monitoring, we have more parts and more space. So if we compromise the board, it would be greater than another board which is with the boost converter technology. So now we have a flyback, and the previous one was boost converter, and so it would be a bit bigger of the size. And the test which I've done last week, I have a bit less, or the new board is a bit less energy inefficient. The new one has only an efficiency up to 71% over one charging cycle. So I started measuring when I started boosting. So the capacitor was empty, and up to the capacitor was full, I measured and I said, okay, this is my energy efficiency over one charge cycle. And the data which I measured was 26 volt input and 330 volt output. And the time to charge about 16 seconds. But I had some problems with one transistor, and I had to exchange it. Maybe there are 1 or 2% efficiency which I can get. So maybe up to 73, 75 for the new board. Yeah. And the future work, we will change the layout so that we can use pluggable components to adjust the output voltage and speed, and implement, or we had from the old board, we can use some code to communicate via Canvas, but for the new board there's the communication missing, so we had to implement the code in software to communicate via Ethernet. That's also had to be done, and the tests for voltages up to 450 volts or up to 500 volts have to be done, and the different charging speeds also had to be tested. I just tested charging speeds between the 0.7 amps in average up to 1.5 amps in average. They both work, but I didn't get the maximum speed with 5 amps in average. So if you want to use it or want to look at the code or look at the PCB layout, you can find it on GitHub. It's open source. You can use it. You can develop it further, yeah, or ask or do whatever you want.
Can you go back to the new system schema? Is that one?
Yeah.
Okay, that charge I see as a feedback, as I said,
Yeah.
is the final voltage for that charger fixed? Because you said something about changing a register divider to adjust the final voltage.
That's fixed, yeah.
That's fixed.
We have an input, feedback input pin. I think it's up to 1.3 volts, and if it's above this voltage, then the charge IC stop working. Or not stop working, but stops boosting.
And did you consider the possibility of using for instance, optical isolated, configurable register divider, because that's also that possibility, and then configure the final voltage through software, or even the speed of charging also through software, because it would be easier.
So the voltage at which you can boost, you can at one time put, or you can adjust manually with the plug-in box. And we also have a monitoring line to the MCU, and you also can start and stop the boosting via software. So if you want lower output voltage, you can set by the microcontroller. So then the microcontroller also can use or can do some string of control. So if you say, okay, the maximum voltage is 400 volt, but we only want to use 300, then you can regulate by the microcontroller. But
the hardware regulator is for safety reasons in that case?
Again, for safety?
The maximum voltage hardware regulation that you do using
for safety and for more precise. I think the MCU only had 10 bits accuracy of their ADC channels, and so if we have accuracy and
you can solve that by subtracting 300 volts and then use the full resolution above.
Yeah, okay.
Okay. I understand that. Thanks.
Yeah.
If you switch out the power supply, will the capacitor discharge automatically?
Yeah.
Automatically.
That was one of the security or safety things,
Okay.
which was one big point that there's no voltage left on, or no power left.
Okay, but the MCU is software or something
Again?
developed. The MCU, but you made with MCU.
The MCU, there's software running on it. Yeah.
Okay.
But it didn't control the discharge, or it can release the discharge, but if you unplug the power, then the discharge automatically.
Okay.
What's the current which is flowing to the kicking coil? The maximum current?
I didn't measure, but I think it's up to 50 amp.
Okay.
So if we, it belongs how long or how far we want to kick.
Mm-hmm.
I think the maximum time we switch the switch is up to 40 milliseconds, and at the end I think we have up to 50 amps.
Okay. And that's also how you control it. So you don't use PWM to control it.
Again?
You don't use PWM to control the current through the kicking coil. You also
No, we don't use. We only switch it on and switch it at the end.
And does that result in reproducible shots?
Until now, we don't have such a reproducible shot, but we hope we'll get it now. Before on the old board, they had also some problems with the switch or with the gate or with the gate resistor of the switch, because it was quite big. We found it out in the last event in Leipzig. The one who designed the old board put a 1K or 10K resistor in the gate line, so the switching time was even longer than it should be. So we had some problems with some broken parts, and that maybe also was the reason that it wasn't so reliable and not so repeating.
When would you call two shots reproducible? I mean, if you would compare two shots, how would you decide that indeed this board shows reproducible behavior?
We had one. We used a laser scanner for it, and we laid it on the. We tried it on at 90 degrees, and we calculate, or we measured one shot, and then we can get at the distance and the height, and we want to do, or we did it for the shots for times between, I think. I think 1 millisecond up to 10 milliseconds up to 40 milliseconds, and then we get we did it before, and then we can do it. We will do it again for the new board, and then we will check if many shoots will have the same curve or have the same distances detected by the scanner.
Yeah, and so what is then the distance where you would decide, okay, this is the same or this is not the same? So what are the requirements on reproducibility? We don't have any values for to say if it's or we don't have any exact values to decide which is now reproducible. But how are you then going to assess the reproducibility?
I think if we are in a range of some centimeters, then we can say it's reproducibility. But for now, we have some shots which goes a bit left, a bit right, a bit shorter, a bit longer, and if we keep hitting one point or one area with a radius of up to maybe 5 centimeters, then we can say it's the reproducibility we want.
Yeah, and why do you choose 5 centimeters and not 10 or 15 or 20?
That's only a value which I know decide. I don't have any.
Okay, now maybe it's good to think about a measure that relates to the task that you wanted to do.
Do you have a requirement for the reproducibility of the shot?
No. But I was not saying that I was assessing reproducibility.
Yeah, of course. But I was wondering if
actually, one of our students is looking into that right now as well. And then, of course, I ask the same question.
Of course, yeah.
So I mean, it would be good to have some specifications for that,
Yeah.
so that you can really decide it's either reproducible or not.
What's the capacity of the capacitor?
It's 8.2 millifarad.
8.2.
So we have a maximum at 330 volt. We had a maximum energy of 450 joule.